In this video, we are going to look at a simple one-dimensional latent variable model, the exponential normal model. We will see that its posterior is intractable, but we will find a remedy by the help of a surrogate posterior, which we're going to fit using variational inference. We're going to do all the optimization steps and an implementation in Python. Hi and welcome to this new video. Variational inference can be challenging to understand at first, so I think it's a good idea to look at this rather simple example of the exponential normal model. The agenda for this video is that we will first try to be naive and find a true posterior. We are going to fail because in this particular model we have to solve an intractable integral. Then we will look at an interactive visualization where I want to show to you the joint distribution, which you also might have seen in the previous video. Then an hypothetical posterior, because numerically we could obtain posterior values, and also a surrogate posterior. Then we will use the idea of surrogate posterior to optimize our evidence lower bound. So in other words, here we are doing variational inference. And for this particular model, it is super cool. If we propose a specific surrogate posterior, we get a closed form optimum. And in the end, we can have a quick demo with TensorFlow Probability, which also again highlights the difficulties in variational inference. So let's get started. First point, finding the true posterior. Let me change the color here. And I first want to start with recalling on the joint distribution. So the joint distribution. For this, let us look at a directed graphical model once again. And here we said that we have a latent variable Z and an observed variable X. This latent variable Z shall be distributed according to an exponential distribution with the lambda parameter fixed to 1. So we could also say that this one has a deterministic parameter of lambda 1. And then our latent Z enters the X, and the connection between the two is that the mean of the normal distribution that is used for the probability on X is going to have the Z value. The standard deviation, or also variance, of this normal distribution will be fixed to 1. So we will have another deterministic variable here, and then let's fill that in. So here we had the lambda equals 1, and here we had the sigma equals 1 enters here. And then for completion, let us note down the functional form of both the exponential and the normal distribution. The probability of Z, or in other words, our prior, was an exponential distribution on Z with the hyperparameter lambda fixed to 1. And if we write down the functional form of it, this is a conditional distribution, so it is exponential of minus Z if Z is greater or equal 0, and it is 0 elsewise. And this lambda would be here and here, and since it is 1, we can just neglect it in that particular case. This condition can equally be represented by the help of an indicator function. So we could also say that is the exponential of minus Z multiplied with the indicator function that Z has to be greater or equal to 0. And this indicator function basically says that if the condition is true, it is 1, and if the condition is false, it will be 0. So this is the indicator function, and by this we're just replacing the conditional statement. Then we also have a way to express our likelihood. So P of X given Z, and this one was just the normal distribution. So this is the normal distribution over X with the parameters mu being given by Z, and sigma is fixed to 1. And then we can write down the functional form. So this is 1 over the square root of 2 pi. So there would be a sigma in here, but since it is 1 and multiplying by 1 does not greatly alter the solution. So let's keep it that way, and then multiply with the exponential of minus 1/2. And here we would again have a sigma squared. So we can also get rid of that here. And then we have the X minus Z in brackets squared. And recall this Z here is a placement for mu. So basically the exponential distribution is defining where our normal distribution is going to be centered around. Well, then we can use the factorization of our directed graphical model in order to express the joint distribution, so P of X and Z. Then we get the multiplication, so let me note that down. So this is P of Z multiplied by Px given Z. So it will be the exponential of minus Z multiplied with the indicator function that Z has to be greater or equal to 0, multiplied with 1 over the square root of 2 pi times the exponential of minus 1/2, and then X minus Z in brackets squared. So that's a joint, which is great. Now let's try to find the true posterior. And for this, we want to recall Bayes' rule, which allows us to express the posterior, so p of z given x, as the joint, so p of x and z, divided by the marginal. And the difficulty here is that, I mean, of course we have the joint distribution, that's fine, but we don't have this marginal here. So we don't have that, so we don't have the marginal. The reason we don't have it is because it is intractable. So because it is intractable. We analyzed that also in the last video, but I just want to note it down once again, because p of x is the integral over z, and z shall be going from 0 to infinity in order to get rid of our indicator function of the exponential of minus z times 1 over the square root of 2 pi times the exponential of minus 1/2 here x minus z squared and dz. And there is no closed form solution to this integral. So this one is intractable. So this one is intractable because there is no closed form solution. So no closed form solution. And this also makes sense if you've ever worked with normal distributions, because that would require the error function. So requires the error function, ERF function, and that's a function that cannot be given in closed form. I mean, you can find it in tabular data, but there is no functional expression for it. And that makes it an intractable integral. And as a consequence, if we don't have a normalization constant, we also don't have our posterior. I just want to try another route here. So because sometimes in analytical derivations of posterior, you might see that we take a way where we first go proportional to the joint and then do some modifications, and then we identify a functional form and I say, wow, crazy, we have seen this functional form before, and then we can have the normalization constant based off our knowledge on the potential distributions there are. So I want to write that down. So let's say, let's instead go via the proportional, and that means that the posterior, so p of z given x, is proportional to the joint of p of z and x, or x and z. The order is not important here. And I hope this is also one of the big takeaways from the previous video where we looked at the challenges in variational inference, in that we can already use the posterior if we fix it to the data in order to evaluate which latent random variable, so a concrete instance of a random variable, is more probable. And we looked at it in terms of images. Let me give you another example. So if x is an image and z is some latent information in the image. So for instance, let's do an even simpler example. You have images of digits, and the latent information could, for instance, be the digit. So the digit is 0, 1, 2, 3, 4, all the way to 9, and x might be an image of it. And if you have an image which almost looks like a 9, then the probability of a 9 as a latent variable and the image of a 9 should have the highest probability. Whereas, for instance, a 4 maybe should look a little differently since it is having like straight lines instead of really hand-drawn arcs. I hope that made a little bit of sense. Anyways, let's continue on that. I think this is so crucial that I just want to write it down once again. So the posterior is proportional to the joint, especially when we fix it to the data. And this already allows for maximum a posteriori estimates. So we could already use the joint for doing these map estimates, but here we are interested in full distributions. So we want to go the way and finding those distributions, and if we don't get them, then we want to use surrogate distributions. That's what VI is for. Okay, long story short, let's do that. So I want to change the color here again, and then we can say p of z given x is proportional to the exponential of minus z. And then we have the indicator function that z is greater or equal to 0. And since we have a normalization constant here, I will just kick that out. So because we are working in terms of the proportional anyways. And then we have our exponential of minus 1/2 of x minus z in brackets squared. Let's merge these two exponentials, because since we are multiplying them, the exponents can be added. So this will be exponential of minus z. And let me also expand this square here, so the binomial formula. And then we get minus 1/2 x squared plus xz minus 1/2 z squared. And then, of course, we keep our indicator function, z of greater or equal 0. And here we again have a term which we can get rid of in terms of the proportional, since this is a probability distribution over z. and x is some sort of given. It is a constant in that sense. And so we can work in terms of the proportional again and just have the exponential. Let me also rearrange a little bit in here of minus 1/2 z squared. And then we get plus in brackets x minus 1 multiplied with z. And then we have the indicator of z being greater or equal to 0. Then we can complete the square in here. So this is a typical operation in those kind of exponentials with squares in them. I will have a video linked here. If this is a little strange to you, then please take a look. It's a rather straightforward technique from linear algebra. And essentially this will result in the exponential of minus 1/2. And then we have a z minus, and brackets x minus 1. And then closing brackets squared for this. And then we keep this term here in order to have the equation correct and the indicator function, of course, after the exponential. And again, this will just be another constant, so we can work in terms of the proportional and have exponential of minus 1/2 z minus x minus 1 in brackets squared, then another closing brackets for the exponential multiplied with the indicator function. And if I now highlight one thing, then probably there should be a bell ringing in your head. So if I say this is a mu, and then you look at it sharply and see exponential of minus 1/2 z minus mu in brackets squared, oh, that looks like a normal distribution. So I want to highlight this here and say that's a normal distribution. That's amazing. So we found a distribution we know, and the good thing about doing the posteriors in that way is that we can then get the normalization constant. But now there is the big difficulty. We still have the indicator function. And so we only have a normal distribution for z greater or equal 0. So, but only for z greater or equal 0. And that is causing a lot of trouble. Because now our normal distribution is not going from minus infinity to plus infinity, but rather it is going from 0 to plus infinity. And so we can't use the original normalization constant that we already know. Let me draw this for you. So let me have maybe this chart. So we have a set, and then here we have our probability. And then let's say, for instance, we have to fix our data. So this is kind of the prerequisite, of course, if we want to use our posterior. So let's say, for instance, we have an x of 1.5. So let's say our x is 1.5, and this then moves the mu of our distribution. It's a little weird, so maybe here. So we then have a mu of our posterior distribution. So let's have it like this, and then I just want to try to get a good normal distribution. So this will be now over the entire space. So it's a little getting ugly, but I think you get the point. And the important thing is that this left half of our domain, or of this real valued axis, can actually not be used. So instead, we will be having a distribution which looks like this. So it is following the shape of a normal distribution, but only towards the right. And as a consequence of this, these areas here have to be compensated on the right and have to move up our distribution in order for it to fulfill the normalization condition, because this area here has to be 1. So let's say the area here has to be 1, because that is the definition of a probability distribution. Now there is the interesting thing that the normalization that we would need in order to get the area to 1 was exactly the marginal. And see, that's the integral here. That's the area under the curve. So let me say that is the area under the curve. And of course it is sufficient to just integrate from 0 to infinity, since the values that are smaller than 0 will be 0 anyways, or there will be no area under the curve. And I think that's an interesting observation, isn't it? So both ways. So first just by Bayes' rule, and then also using the trick with just going via the proportional, yields an functional form, but we can't find the normalization. And this normalization is crucial. I mean, it is crucial to have a full probability distribution. As said, if we're just interested in a maximum a posteriori estimate, then our joint is already fine. But we want to have a full distribution. So well, then we are kind of doomed and we have to look into variational inference. Now let's look at a visualization that is a little bit better than my hand-drawn images. So here on the right, we see 3 different probability density functions. For the beginning, let's just look at the joint distribution. So this is also the one I've drawn to you. On the left, we can select the observed x value. So for the simplicity, we will just have one data point and we can move it around. I think we had 1.5, right? So and let me deactivate the other 2 again. And here you see what I wanted to show to you. We have a normal distribution like this, but it is only a normal distribution for set greater equal 0, and it is 0 before. And as a consequence, of course, the area under the curve is not 1. So I have evaluated it numerically here or using the arrow function. And it is about 0.25, so about a fourth. In order to get a full posterior distribution, we would have to normalize it. I mean, we can do that, and that's what you see here. I put that in quotation mark, a true posterior. So you see that its peak is about 4 times as high, but qualitatively it has the same shape. So this one is just normalized by the area under the curve. And now you might say, hey, well, great. Now we have probability distribution. Why are we doing variational inference then if we already get an approximately true posterior by just normalizing the joint? And the difficulty is that this normalization is getting really, really expensive once you look at realistic examples. So here it was doable because we are in 1 dimensions and it is a rather simple application. But if you, for instance, have 100-dimensional latent spaces, you tend to run into a lot of troubles that are referred to whenever you do quadrature in those high-dimensional problems. And so there it might be worthwhile to do the variational inference to avoid this. So here, as said, it's possible, so just that we can have it here. And this should also highlight again that the joint, it's proportional to the true posterior. Between those 2, so in this particular case, is just the factor of 4. And of course, this varies depending on the data we have. So for instance, if we, let me also remove the surrogate again. So if we are at 0.9, then it doesn't look like a normal anymore that much. So maybe if you also go to other values, I think you get the picture. You can play around with this visualization yourself if you want to. The link is in the video description. Okay, but let's go back to 1.5 and now let's have a look at the surrogate posterior. So this now might look a little strange. What is going on here? And remember, the idea of variational inference was to find distributions that are close in their qualitative behavior to the true posterior. And here this true posterior has this some sort of a mixture with normal and the indicator function. So what I used here for surrogate posterior is another exponential function, or exponential distribution to be precise. So that is the same functional form as the prior, which is just a coincidence here. I mean, there is no relation why I'm using the exponential, except for the fact that we're going to have a closed form solution later on. But the idea of variational inference is now to find this distribution which fits the true posterior the best. If you recall the intro to VI, this is done by maximizing the ELBO. Here in this visualization, I already portray the optimal exponential distribution for you. And you also see that it is changing based on the x value. You, of course, could argue that there is a considerable mismatch between the true posterior and the surrogate posterior. But the surrogate posterior brings many advantages that we will then see in our Python demo towards the end. So the next task for this video is to propose the surrogate posterior and then do the optimization for variational inference. So welcome back to my terrible hand drawings, and we're going to leave them behind to move on to our remedy. So again, as said, we can't have the true posterior. I hope that got clear. If there's something unclear, please leave a comment. But now let's find our remedy. So the remedy is going to be a surrogate posterior. So a surrogate posterior, and we coined it Q of Z. So this will be just a distribution over Z, but of course it is dependent on the x values of the data. And recall, the Q of z was found by the optimization problem by saying Q of z is the arc maximum over the elbow on Q. So this one here was the elbow or the evidence lower bound. And I just want to recall that. So L of Q was given, so we could either express it in terms of an expectation or an integral, but let's have it as an expectation here. So the expectation of z distributed according to Q of z over the logarithm of the joint distribution over z and x being fixed to the data divided by Q of z, so the surrogate. And let's close that down. Here this also shows that for the elbow to work, we need some data. So we need some data. And for example, here we will just use one data point. So let's say data is here, I want to have x0 being, let's say 1.3. Why not? And this data is of course crucial since otherwise we would still have a dependency on x, which we don't want. So this x dependency is already cut out by fixing the joint to the data. And now I think one point that is probably also a little difficult to understand conceptually, first let me add the start here, is that the maximization problem or the original maximization problem in the variational inference is a variational optimization problem. So what we have here is a variational optimization problem. And variational refers to calculus of variations, and this means we are optimizing over functions. So that means we are looking for any distribution, any functional form which comes as close to the true posterior as possible. And let's be honest, that's difficult. And difficult is probably an understatement because for real-world applications, this will again be impossible. And so we awaited so many intractable avenues to then end up at another impossible optimization problem. The usual remedy here is to introduce a parametric distribution. So let's introduce a parametric distribution. So in other words, from now on, we are no longer looking at finding the optimal distribution and its optimal parameters, but we are just proposing one distribution and then trying to find its optimal parameters. And here I want to use another exponential distribution. And as said, this is unrelated to the prior exponential distribution. I mean, of course, it helps that the prior is also exponential in the derivations later on, but theoretically, if you want to apply VI for your real-world cases, you can choose any distribution that, of course, fits your assumptions. So it should be a distribution that, for instance, should be a discrete distribution for discrete variables. I think you get the point. So that makes our surrogate posterior a parameterized distribution by the parameter theta. So Q theta of z is going to be an exponential distribution on z, and its lambda parameter is going to be theta. So that's just a little bit complicated to saying that here we have a distribution that is theta times exponential of minus theta z if z is greater or equal 0 and 0 elsewise. And we can again use the indicator function. So we will get theta times exponential of minus theta z times the indicator function of z being greater or equal to 0. And now if we plug this proposal into the optimization problem over the elbow, we get an optimization problem over theta. So we can find a theta star, so the optimal parameter to this distribution, as the arc maximum over all theta from the positive real-valued numbers. So this is a restriction on the what the parameters for an exponential distributions are. Never mind, so it's just a technicality. And again, we will have our expectation over z given by Q theta of z on the logarithm of P of z and x being fixed to the data divided by Q theta of z, and then closing brackets here. And this will now be the evidence lower bound. So that is again the elbow, but now this elbow is a function on theta. Given different theta values, we will have different elbow values. And now we want to find that theta which maximizes our elbow. And the next steps that we're going to do are plugging in our proposal distribution as well as the joint fixed data that we've seen before. And then we can actually find the closed form optimum. But I just want to leave a couple of remarks here, because of course, again, in many real-world applications, you won't find a closed form optimum. So for instance, if you look at variational autoencoders, one of the next videos, you will see that of course you can't optimize that analytically, but then you have to approximate the elbow. So I just want to leave that here as a remark. So in real-world applications, and an example is of course a variational autoencoder. So for instance, VAE, you have to approximate the elbow by sampling. So sampling is one strategy to approximate it. And since you then say, well, we can say that an expectation over a distribution of something is we sample a little bit from the distribution, and then we will see that. You will see about that in the video on the variational autoencoders. But this might raise the question, hey, earlier we looked at a true posterior that it can be found if we numerically normalize our joint distribution. And for this, we had to solve an integral or a quadrature, which I said is impossible to do in high dimensions. And now you could also say, well, maybe this might also be impossible to do in higher dimension. I mean, it's a fair concern. The arguments against this are, first of all, that usually the surrogate is easier than the true posterior. I mean, if it exists. So let me say that the surrogate is simpler than the true posterior. So that kind of makes it easier, but probably also with a simple posterior sampling in 100-dimensional latent spaces might be rather difficult, which is again a fair concern. And the point here is that in real-world applications, it kind of has shown that you tend to not need too many points. You don't need an 100% or 99% correct approximation of the elbow. Usually in those optimization problems, you can do stochastic analyses in order to show that already a couple of samples are sufficient to get a decent convergence in your optimization problems. And this is something you can't have when you really have to get your true posterior by finding the normalization constant. So that's again an argument in favor of VI, but I think it will become more clear once we look at variational autoencoders. So again, this was just an important remark, because otherwise it might give you the wrong feeling that everything can be solved in closed form. Okay, let's finally do what we're supposed to do. Let's take our elbow and write it down. So we will have the elbow, which now depends on theta. And as said, it's going to be the expectation of z distributed according to q theta of z over the logarithm of p of z and x being fixed to the data minus the logarithm of q theta of z. And I just split out the fraction here by using the logarithm rules. And then let's plug in what we have. So let's keep the expectation. And for the sake of simplicity, I will just ignore that here, but keep that in mind. That is valid for all subsequent expectations. So we will have the expectation on the logarithm of our joint. So let's take a look again at the joint distribution. So where was it? It was here, I think. Yeah, here we go. So this is our joint distribution. So we have the exponential, then the indicator, then this one, then this one. So let's apply it step by step. So the logarithm applied to the exponential will give us minus z. Then we will have the logarithm applied to the indicator function, and that will be 0. I will show you in a second why that is the case. Then we will get minus 1/2 logarithm of 2 pi. And that's also a classical finding if you do maximum likelihood estimates, for instance, for normal distributions, etc. Then the logarithm cancels again with the exponential, and we get minus 1/2 x0 minus uppercase z and bracket squared. And again, recall this x0 is this one data point that we have. So here we said it's 1.3. Okay, And then we have minus the, so let me minus opening closing brackets. And here we have the logarithm of our proposed surrogate posterior. And this one was in this particular form here. So we will get first the logarithm of theta, then the logarithm of the exponential. This cancels, so we have minus theta z, and then we can get the logarithm of the indicator gives us 0. And I just want to show you why that is the case. So the logarithm of the indicator function of z being greater or equal to 0 is going to be the following. So the indicator function was 1 if the condition is true and 0 elsewise. The logarithm of 1 is 0, and the logarithm of 0 is minus infinity. So it is 0 for z greater or equal to 0 and minus infinity elsewise. And since our expectation will be over z, and z is always sampled according to an exponential distribution, which never takes values smaller than 0, the only accepted value will be 0. So in that particular case, the logarithm of the indicator turns to 0. Okay, let's go on and just rearrange a bit. So we have the expectation of minus z. Then we will keep minus 1/2 logarithm of 2 pi. Then let's also expand the square again. So minus 1/2 x0 square plus x0 capital Z minus 1/2 capital Z squared. And then we have minus logarithm of theta plus theta Z and then closing brackets. Okay, so now we have to make usage of the exponential distribution and its properties of expectations. So I just want to quickly note that down here. So this is something, I mean, you don't have to know that by heart. You can look it up on Wikipedia, for instance. So the expectation of Z distributed according to an exponential with the parameter lambda on something is going to be just this something. So if there is no Z in there, the expectation of Z, same situation with a lambda, of something, if there is only one Z in there, is going to be 1 divided by lambda. And the expectation of Z with this, if there is something in front of a Z squared, is going to be 2 over lambda squared. And let's apply that. So let's first start with those that don't have anything. So we have the minus 1/2 log 2 pi. We have this one and this one. So this is basically referring to here. So let me get the equal sign in white color. And then we just get the values of this, because I mean, the expectation of something over something which is not included in that will just be the value itself. So we have minus 1/2 logarithm of 2 pi, minus 1/2 x0 square, and then minus logarithm of theta. Okay, next up we have those that include one Z, so this one, and this one. And these one are just divided by lambda. And recall, lambda in our expectation is theta. And of course I forgot the dots here. So basically the set, of course, is kicked out since we do the expectation over it. In essence, that is kind of an integration over it. So here we are getting minus 1 divided by theta. Then here we get plus x0 over theta. Oh, of course not lambda, but it's theta. And then here we get plus theta divided by theta. And then we are just left with expression here. So this is the last one. And this gives us just 1/2 and then 2 over theta square. And then let's simplify a little bit. So here the theta and theta cancels, the 2 and 2 cancel. And then we can write it down properly once again. So we have minus 1/2 logarithm of 2 pi minus 1/2 x0 square minus logarithm of theta minus 1 over theta plus x0 over theta plus 1 minus 1 divided by theta squared. Okay, and recall what we just found is the ELBO in terms of theta. So it's a function which is dependent on theta, so we can have different theta values, And these different theta values result in different ELBO values. And the task of our optimization is to find this one theta value, or in the best case, one theta value, which gives the maximum ELBO, so the maximum evidence lower bound. And since maximization, I mean closed form maximization, is taking the derivative and setting it to 0, we can ignore all these terms which are just constant. So we can kick out that one, we can kick out that one, and we can kick out that one. So we then get something that is the evidence lower bound up to an additive constant. So we have minus logarithm of theta plus x0 minus 1 over theta. So I just merged these two together, minus 1 over theta squared. So here we go, and that is the closed form ELBO. Amazing. So we found the closed form ELBO. Isn't that cool? Of course, as said, you don't find that in real world cases, but it's cool that we have it here. But with a closed form ELBO, we can then find our theta. So recall the theta star was the arc maximum over all thetas from the R positive over the ELBO. Okay, well, how can we find that? So let's just take the derivative and set it to 0. So we will do dl by d theta. And the last steps before we have our closed form solution, so bear with me, derivative of logarithm of theta with respect to theta will of course be minus 1 over theta. And then here we have the derivative of theta to the minus 1, which gives us minus x0 minus 1 over theta squared. And then here we have the derivative of theta to the minus 2, which gives us plus 2 over theta to the third power. And this one has to be equal to 0. Let's multiply with theta to the 3 in order to get it out of our denominator. So we will get minus theta squared minus x0 minus 1 times theta plus 2 is 0. Then let's multiply with minus 1 to get theta squared plus x0 minus 1 times theta minus 2. And then we just apply the PQ formula. And we get theta 1, 2. So because we have two possible solutions here, which is this one halved and with a negative sign. So minus x0 minus 1 divided by 2 plus minus the square root of x0 minus 1 in brackets squared over 4 plus 2. And now we find two optimal values. And now we have to take a sharper look because we actually had a constraint. So the constraint was that theta is only allowed to be positive. And so basically what we have here, this one will be a negative value. And if we then subtract a value from a negative value, we're going to have something that is going to be even more negative. So we prefer to have the positive sign, at least for the simple cases we're looking at here. And then we get our theta optimum as minus x0 minus 1 divided by 2 plus the square root of x0 minus 1 in brackets squared divided by 4 plus 2. And here we go, that is our closed form optimum. Again, to remind you, that is the optimal parameter to our surrogate posterior. To highlight this once again, it depends on the data. So the surrogate depends on the data. So the surrogate, or in other words, the optimal value of the parameter to the surrogate depends on the data. And that of course makes sense because our surrogate is a replacement for the posterior. And the posterior was P of Z conditioned on X. And so there must be some sort of a relation from the data or from the observed values X to the surrogate. And that's what we find here. Isn't that beautiful? Okay, finally, let's look at an example in Python by the help of TensorFlow Probability. So I already imported TensorFlow, TFP, I made a shortcut for the distributions, and I activated the interactive mode of Matplotlib. First up, of course, we have to translate our directed graphical model of the simple exponential normal model into TFP, and we want to create a joint distribution by the help of a coroutine. So let's create the generator. So define in order to get a function, and I want to call this exponential normal model, and this one takes a lambda. Unfortunately, lambda is already reserved, so I will just use lam, and it takes a sigma as the hyperparameters, which are of course given, but I want to have them here as arguments to the generator. Then we have a set, which is our latent node, and it is a node in our DGM, so let's do yield. And then we have to indicate it as a probabilistic root node by doing tfd.joint distribution coroutine.root, and then let's apply this to tfd.exponential, so because that is the distribution of our latent variable, and the rate of the exponential, so that's the parameter to it, shall be the lambda. And then we have to activate a parameter that is called force props to 0 outside support, because for performance reason, TensorFlow Probability will give us a probability for values smaller than 0, although mathematically the exponential distribution should be 0 there. And let's give it a name latent mu, because it's the mu to our normal distribution, which we are going to define next. So x is going to be yield, and then we have tfd.normal, and it takes a location, which is going to be according to the set or the latent mu. Then it has a scale, which is according to the sigma. And then let's just give it the name, which is the observed x. Let's close that down. And that's our generator. I will just quickly clear the screen, and then we can define our joint probability density function by saying tfd.joint distribution coroutine on the exponential normal model, but we have to first fix the parameters. So I will just create a lambda function without any arguments, which calls the exponential normal model with lambda being set to 1 and sigma being set to 1. So this is because we made these assumption or the same assumptions in the derivation. And then we can already close that down. That's our joint PDF. Let's look at it. So it has the latent mu and observed x. Theoretically, of course, if we were to sample it, TensorFlow Probability is not aware of variables being latent. So we have to handle this manually because it would say sample a mu as well as an x for us. Either way, now we have some data observed. So let's say observed data point. And for the sake of simplicity, this was 1.5. I think we chose 1.3, so let's stick with that. And then we can create a function, which I want to call joint fixed to data. And here, this will be a function which takes an set and then calls the joint PDF probability function on set and the observed data point. So it's basically a function that whatever set value you will call it with will always call the joint with the observed data point. It's kind of a wrapper that we did in computer science speak. And in the end, this is fixing the data to the joint. So if we now call this function, for instance, on 2.0, we get the probability of 2.0 in the joint sense. And this value is proportional to the posterior. And let's see, I think negative values should result in 0 because we correctly used the parameter, the argument to the exponential function. Okay, let's quickly create a plot for this joint fixed data. So I want to create a set range by saying tf.linspace from -5 to 5 by 1,000 points. And we have to cast this into tf.float32 because that's the default precision in TensorFlow Probability. So I will just do a tf cast into float32. And then we can get a probability range by just calling the joint fixed data on the set range. So the broadcasting works correctly here. And then we can plot that, plot set range and prop range. And here we go, that's our figure. I will just keep that in the foreground. And that's also what we've seen in the interactive visualization earlier, that all the probability of values smaller than 0 is 0. And then behind 0, we have something that kind of looks like a normal, but since it is cut off it is not a true distribution because the area under that curve does not add up to 1. We can also quickly check that by importing the integrate package from SciPy and then doing integrate.trapezoid on the x being the set range. So this is basically just a numerical quadrature under the curve here, and y being the probability range. And you see this area under the curve, I mean, at least until 5 is 0.277. And I hope you believe me that there, of course, will be still some area, but the major area of this curve is until 5, and afterwards it will be negligible. So in the end, it's not normalized. As said, we could normalize it now, but I will leave that to you. More interesting though is to now introduce our surrogate posterior. For this, I want to first compute its parameter. So let's say optimal surrogate parameter, which is going to be first minus observed data point minus 1 divided by 2. So this was the quantity in front of the square root, plus tf.square root on the observed data point minus 1 in bracket squared divided by 4 plus 2. Okay, what is the value? So the optimal value is 1.27. Then we can get our, or maybe let me first clear the screen, and then we can get our surrogate posterior, which will be a tfd.exponential, and this one will have a rate according to, well, this is the parameter as it is named in TensorFlow Probability, according to the optimal surrogate parameter. And then we can also call it on the set range. So we get a surrogate probability range is going to be surrogate posterior.probability on set range. And let's also quickly plot that. And here we go. I think, yes, I did something wrong. Of course, yeah, that should be surrogate prop range. Okay, here we go. Okay, I forgot to add this parameter. Well, happens. So there should be this force props to 0 outside support being true. Then let's get some new probabilities, clear the figure real quick, and let's do a plot of the prop range first, and then plot again. Okay, amazing, finally. So here we see that, of course, the surrogate is an exponential distribution, and the joint was this kind of cut-off normal distribution, and the true posterior would also be this kind of cut-off normal distribution, but it's impossible for us to normalize it. And this is also the reason this looks way taller. It's just because this joint is not normalized. Okay, that's the end of the video. I hope this simple scenario for variational inference was insightful. I would encourage you to stick around for the next videos, because it's going to be really nice on variational autoencoders, which is just moving variational inference to the next level with neural networks. It's going to be really exciting. A big thanks to all the Patreons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you find the link to the Patreon page down in the video description. So if you enjoyed the video, then please consider liking and subscribing. There is more awesome content like this on the channel. Here you will now see similar videos, and I hope to see you in one of the next videos.